Morning, everyone. Hello. Thank you for joining us on day 2 of our Explainable AI conference. And it's nice to see so many faces from yesterday coming as well. So we've got another fantastic workshop led by Moises today, who's very kindly joined us from the University of Guadalajara. And he's going to be going through genomic sequence classification using PyTorch and other open source models. So without further ado, I'll pass over to you. And for anyone watching online as well, if you've got any questions throughout, we'll be monitoring the chat and asking them for you. So enjoy.
Thanks. Good morning, everybody. How are you today? Good? Did you sleep well? Kind of. For me, it was kind of. Well, thank you very much for coming today to this workshop, which title is Exploring PyTorch and Transformers for Genomic Sequence Classification. As they already said, my name is Moises Sotelo Rodriguez. I'm coming from Mexico, from University of Guadalajara. That is in Jalisco. Have you ever visited Mexico or Jalisco? Well, Jalisco is where mariachi and tequila comes from, so it will be a really nice place if you ever plan to visit Mexico. Well, let's start with a question. Have anybody of you ever used deep learning techniques for your research? No? Yes, some. Okay, one hand raised, more or less, okay. Thank you. For those people who implemented deep learning techniques, was it easy or complex? Easy, okay. And well, the next question will be, what difficulties did you encounter with when implementing these algorithms for your research? Sometimes these kind of things are really technical or really hard to implement because there is a lot of code, and when you try to execute these models, there is an error, and since these are like Lego blocks, it's really hard to debug these errors. So, well, it's kind of complicated sometimes. If you don't have a lot of coding experience, it could turn into a really hell, this implementation workflow. But that is the objective for today, to learn how to implement these techniques. And you will have the code. I will share with you a Jupyter notebook in Colab, so you can execute everything. Everything is already done. So we will just go through the process. So this is today's outline. First, we will see a basic introduction to deep learning theory, some cases of deep learning in genomics, right? Deep learning implementation workflow with HuggingFace, which is a library that has a lot of functions, helpers that make it pretty straightforward to implement these tools. We will see how to evaluate these models, and finally we will see how a manual implementation with PyTorch looks like. So first, this is HuggingFace's logo, and we will see how to implement these models. So to do this, I ask you to scan these 2 QR codes. This one, or the one on your left side, is for the Google Colab Jupyter Notebook. And the second one, for those who would like to run or execute these algorithms, the QR code on your right side is a link to the GitHub repository where everything is stored. Could you open the corresponding links already? Yes? No? Who wasn't able to open these links to this moment? Okay, I guess everybody already, oh yeah. So let's wait a little bit more. Okay. Okay, I guess everybody was able now? Or has anybody else is having difficulties to open these links? No, okay. So let's go straight into the Jupyter notebook. This is, this is what you should look right now, right? Am I correct? Okay. So first of all, we are going to do a little bit of configuration. As you might know, deep learning models and many other machine learning models require a lot of computational power. So thanks to the Google Colab platform, we can, let's say, borrow a GPU from Google. And this is how this is done. Okay, so we can see here on your upper right side a connect button, and next to it an arrow, right? Then we will select change runtime type, yes, and then T4 GPU, then save. And then we connect to the instance in Google Colab. So, well, yesterday we already worked with Jupyter notebooks, but is there anybody here who who is not experienced with Jupyter notebooks or that don't know what a Jupyter notebook is? No? Okay, so we can go straight into the workshop. Well, again, this is the outline for today. We will see the objectives, what is deep learning, some cases of deep learning in genomics, the implementation workflow for these tools. We will see and check the data set that we are working with today. Also, we will train these models in two ways. First, with the HuggingFace's transformers library, and then manually, right? Finally, we will see some conclusions about this workshop, and well, I will leave my contact details. So first, what I want you to learn from this workshop today is first, learn the basic theory of deep learning. We are not going to see many math formulas or something like that. We just want to get the general idea of deep learning, what a neural network is, and basic stuff. Then understand the workflow for deep learning. Yeah, because some people might think that implementing a deep learning model is just throwing a function and it will do some kind of magic, right? But there is some work before to do that. Then deploy a model for genomic sequence classification, first with helpers, as with the HuggingFace's tools, and then manually with PyTorch, right? So what is deep learning? This is a little diagram that we already saw yesterday, just another version of it. But deep learning is a subset of machine learning techniques that uses specifically neural networks, artificial neural networks. What makes deep learning is the number of layers that these artificial neural networks have, right? As the workshops or the people were saying yesterday, we now have deep learning networks with thousands or hundreds of hidden layers, making them more powerful and with better prediction power always, right? So one of the main differences between conventional machine learning and deep learning models is how how much data they need to learn or to generalize the phenomenon we are studying, right? So as well, deep learning can learn from raw data. In this case, will be genomic sequences. There is apparently no any structure within it, but we will see that these deep learning models can extract some information, see some patterns, found any other kind of information.
Share the link for this so the people online can follow along.
Yeah, sure. Here's the links again. Yeah, sure. Yeah, sure. So, okay. Okay, there it is. Sorry. Continuing with these ideas, well, yes, since these models were too complex when they were, let's say, idealized, there was not enough computational power to implement them. So nowadays that we have GPUs, TPUs, and more advanced hardware, it is becoming more and more common to implement these strategies, right? So we can find within this organization of artificial intelligence, machine learning, and deep learning, the deep learning in the most inside part of the diagram, right? Some cases of a study of deep learning in genomics, right? Here is a really interesting paper about deep learning architecture that was able to predict gene expression based only in genomic sequences, right? Afsek and his collaborators developed a deep learning architecture with combining two different architectures, the convolutional architecture and the transformer architecture. They remarked 3 points from their model. That first, it can accurately predict activating or repressive mutations affecting gene expression. Then its predictions are not limited to conserved enhancers, so they can account for variations within those enhancers. And third, it produces predictions independently from the genomic sequence type. This could make it possible, or this could allow us to generate and assess, let's say, synthetic genomic sequences and test and predict what will be coming out from those artificial sequences. The second one is a model, relatively new, which is hyena DNA. This model specifically, they replaced what is called the attention layer or the attention block from conventional transformers for something they call long convolutions, right? So this makes this model capable of predicting for really long sequences up to 1 million nucleotides without losing the single nucleotide resolution. This, this model allows to make more predictions about or accounting for normal evolutional or variation in general. The third one, and the most recent one, is Deep RBAT. This network, to make it short, they were able to do association tests on rare variants that normally within the GWAS studies or genome-wide association studies will be ignored, because these variants are not as frequent as those that are detected within the association test in the GWAS. So this deep neural network was able to perform and somehow do the association tests for these rare variants. Okay. Is there any question up to this point? No? Okay. So let's start with the workflow. These 3 cases of deep learning in genomics is just to show you a little bit of the potential deep learning has within the field of genomics. Maybe within your own research applications, you can think about many more ideas or many more applications for these techniques. So the deep learning workflow goes as follows. First, we will select and curate the data. Since, and for illustrative purposes for this workshop, the data is already pre-processed. We will just download a data set and we will check its characteristics. And well, we will kind of skip that part of the process. Second, we will choose a model. We will download a model from the HuggingFace's hub and then just fine-tune it with our data set. Actually, we are going to fine-tune the hyena DNA model. Then evaluate the model's performance. We will see some evaluation metrics important for to assess the power of these deep learning models and how to translate this into biology. And then finally, interpret the results, right? So first, here is where we import all the modules and libraries. You can also execute this code along with the workshop. Here, there is a little chart that says that this notebook is from my GitHub repository. So, well, believe me, it's just this for this workshop. And okay, here we import or install some new libraries that are not in the Google Colabs instance. And I will explain you why. Here it's where we import all the libraries necessary for the workshop. And as you can see, they are separated in blocks, right? The first block is related to PyTorch, all the building blocks for neural networks, for data preparation and stuff. Second one is for those libraries for data science or data analytics or workflows, to import data, to export data, to calculate some metrics for the models, etc. This one, this one just allows us to download some files from Google Drive. The fourth block, it's for the transformers library from HuggingFace, for the data sets, the evaluation metrics, and for the progress bar. And finally, this one is for the data set that we are going to work with today. So, the data set that we will be working with today is the genomic benchmarks data set. They are a set of data sets that were constructed or built to assess models' capabilities. These are already labeled, pre-processed, and clean data. They are basically meant to, if you do a model or if you program or develop a model, check what are its capabilities, right? And for illustrative purposes, we will work with the human enhancers cone data set. As you can see here, it is here, right? So we will work with that data set. Basically, what we are going to do within the machine learning verboses is a binary classification problem, or we are tackling this problem, right? This data set contains sequences that are or are not enhancers. So first of all, maybe there's people who doesn't know what an enhancer is. for short, it is genomic regulatory elements that influences transcription. You might have heard about another term, which is promoter. And the basic difference between them is the distance they have between this element and the gene they regulate. And basically, these two regulatory elements make the gene to be overexpressed, right? So let's print some information about the human enhancers cone dataset. As we can see here, we have two classes, negative and positive. All the genomic lengths are equal to 500. This means that our sequences are 500 nucleotides long, and we have totally 27,791 sequences, for which 20,000 or around 20,000 are for training, and around 6,000 are for testing, right? As you can see here as well, we have a really balanced data set for both the negative and positive classes. Do you know, or does anybody know in this room, what is the advantage of having a balanced data set? Yes, exactly. It goes. It's the general idea. For example, I like to think that deep learning models are like kids. They try to imitate everything they see, right? If they see something happening more often than something that doesn't happen really often, well, they try to imitate this behavior, right? So in the case of deep learning models or any machine learning model in general, if they see more, let's say, instances of one phenomenon, they will think, or they will make predictions based on that frequency of that data, right? So this will yield into false positives or false negatives, right? So having a balanced data set is always something to account for before training the model, because as they were saying to us yesterday, having good data is what really matters for, well, to develop a really useful model. Okay. So fortunately, the genomic benchmark models offers some functions that make it easy to download the data sets and to split it into training and test sets. Does somebody know why we split this data set into train set and test set? Exactly, yes. Does somebody wants to add something more to that answer? Yes, basically, we will, well, train the model with some kind of data with the more examples as possible, right? But we cannot test the model's capabilities with the same data it was trained, because we will say that it is memorizing or learning the actual structure of the training data set and not testing its capabilities, right? So we have to evaluate the model in data that it has never seen before, right? Okay. So the next code cell is just to print the same characteristics that we were looking at before, just to make sure that we downloaded the correct data set. And here it goes, the actual question of the workshop. In the next code cell, if you run it, it will generate two sequences, right? If you didn't see this part of the code, and you read these two sequences, will you know which one is an enhancer and which one is not? Will you be able to say which one of those is the regulatory element and which is not? Hopefully, with deep learning models, we could say, oh, this one is an enhancer and this is not, right? So that is, let's say, the magic, or why we use deep learning models for these kind of tasks, and why in this example are enhancers. But maybe enhancers have some kind of clinical relevance, right? Because some diseases are related to the overexpression of some kind of gene, or maybe in other kind of situation, these diseases or phenotypes, as we might call them, are influenced by some other regulatory element within the genome. That's why we use, well, that's one of the reasons we use these kind of techniques in genomics or in medicine, biology, biomedical science, etc. Right? So we will check first the model training with HuggingFace. HuggingFace's Transformers library was introduced in 2020, and it is an open source library to make powerful models available for everybody, right? They were first, let's say, tackling the problem of many natural language processing tasks, but eventually received many genomic language models as well. So the basic steps to train or fine-tune a transformers model are, first, since we already have the data set, pick a model from the HuggingFace hub, then select a tokenizer that corresponds to the same model to ensure compatibility between inputs and outputs and the model. Then apply this tokenizer to the data set, define the training configuration. How is it going to be trained? Through epochs, maybe we can select the loss function, and many other hyperparameters. Set up the trainer object, train the model, and finally evaluate it. There is more information of these processes on the HuggingFace website, and we will go to the first step, model selection, right? So HuggingFace offers a wide range of pre-trained models. Does anybody know how or what a pre-trained model is? Basically, a pre-trained model is a deep learning model that has already been trained on some kind of data to get general information about the phenomenon it is studying. In this case, we are going to use the Hyena DNA model, and it was pre-trained on human genomic data to predict the next token, or in biological language, the next nucleotide within the sequence. So doing this, we can kind of assure that the model understands up to some point the genomic grammar, let's say, and it has already knowledge of the structure of the relationships between many genomic elements and how they impact on each other. Right? So if we run the next code cell, we can see here that some stuff is being downloaded. It's just the models configuration files and some other files that the model needs to work properly. And here the first line of code is the models card within the HuggingFace's hub. And finally, the other line initializes the model. It downloads the configuration files and everything the model needs to work. Then, now that we selected the model, we have to select and apply the tokenizer. The tokenizer is basically what makes it possible to convert from, let's say, character sequences to representable numbers or meaningful numbers for the model. Because we know that computers work with numbers, right? If we, let's say, gave them normal text, they couldn't or they wouldn't understand what we mean with those sentences, right? So basically, this is how Alexa, Bixby, or Siri work in the natural language processing workflow. There is something or some kind of transformation that convert our words into numbers or some kind of representation computers can understand, and this task is performed by the tokenizer. And since many LLMs or large language models, they have their tokenizer specifically designed for that model, we will need to use tokenizer and model together so we can ensure compatibility between these two objects. So this is exactly what we do here. We initialize the tokenizer and we define this variable called max length equals to 1024. This is because this is the max length the model accepts as an input, right? Okay. Continuing with this, and to save some steps from the data set we initially imported, there is actually something, or the data set within the HuggingFace hub as well. So we can download it again, and it is already in some kind of a structure. Oh, yeah.
Yes, this max length is the same for each model, or is proper of this data set?
It's specifically for this model.
And
yes.
How do we know the max length?
Oh, the max length? If you go to the models card in HuggingFace, these characteristics are displayed over there.
Oh.
Yeah, it says the maximum length the model accepts, also the tokenizer that it can be trained with, and more data. Yeah. Thank you. Okay. So once we retrieve the data sets or the data set from the HuggingFace hub, we can print it. We can see how this data looks like. And as we can see here, it is contained in some kind of a structure named dataset dict, right? And it is already split in train and test set. And we see the same numbers here, around 20,000 samples in the training set and 6,000 samples in the test set. And we have here two keys, sec and label. What do you think is contained on them? The sequence and the labels, right? So a sequence, let's say some combination of ACTG letters with the corresponding label saying if it is or if it is not an enhancer sequence, right? And this applies for both data sets, or for both the train set and the test set. And here again, we can see just one sample to keep checking that we are, or with what kind of data we are working with. And here we have the identifiers sec and label, what we already said. If we scroll to the right, to the end, we can see that this one has a label of 0, meaning it is not an enhancer, right? So we already know the structure of the data set. It is pretty simple, right? We have a set of sequences and a set of labels, and that's it, right? One of each of these labels is explaining or saying that the corresponding sequence is or is not an enhancer, and that's it, right? Pretty simple up to this point, right? Does anybody? Oh, yeah?
How does the truncation?
Oh, the truncation here, where is it? Here, right? The truncation, if there is a sequence larger than the maximum length accepted by the model, it will be cut to that length. It will be truncated to that length.
From the 5' or from the 3'?
No, to the length of the sequence. For example, our max length variable here is equal to 1024, right? But what if I had a sequence within my data set with a length of, let's say, 2000? This sequence of 2000 long nucleotides will be cut into a sequence of 1024 nucleotides.
Does it cut from the beginning or from the end or from the tail?
It depends on the tokenizer, because some tokenizers can cut the other part is padding, which is enlarge the sequence. They can cut either from the right or from the left. Mm-hmm. It depends on the tokenizer.
You longer, can it make two?
So get two sequences out of that cut.
So instead of like giving the exact length one, you give one long sequence
Mm-hmm.
to make sequences of it.
Oh, I don't think so. I don't think it takes the remaining parts of the sequence as another sequence. I think it just cuts it and that's it. Mm-hmm. Yeah. Any other question up to this point? No? Okay. So after this, we will use the trainer API that HuggingFace gives us. The transformer module includes this helper, and all we need to do is just tell it how the model is going to be trained, right? Here, this is a function to compute a very basic evaluation metric, which is accuracy. And I have to put it here before actually training the model, because after this, we will check its metrics, or we will evaluate how the model is performing, right? So if we if we execute this code cell, we will get anything from output. But this is because this variable will be another input to the actual trainer object, which explains or which tell us or which tell the program how the model is going to be trained. So here we will take as parameters the model that we are working with, the training arguments that we just declared, the train data set that we also declared up here, and the evaluation data set as well. The tokenizer and this data collator. This data collator is some kind of a special object or function for the data set, because again, within continuing this idea that I might have sequences of different lengths within my data set, I can either path or truncate all of them relative to the shortest or longest sequence within all the data set, or I can do this same process, but let's say if I have a batch size of 8 sequences, I will do this relative to the longest or shortest sequence on that batch. Am I making sense? Okay, let's go again. The deep learning models don't take the whole data set as the input, right? We will have to give it a number of examples in each iteration, right? So this is the batch size. The batch size is the number of samples that it's going to go into the model on each iteration. Let's say that I take 8 samples for one iteration, right? I might have sequences of different lengths in that batch. So what I can do to make all of them homogeneous between them is to pad them or truncate them. Yeah? Mm-hmm. The models, they don't accept different lengths of inputs. That's because the input layer is, it has, in this case for this model, 1024, let's say, input variables that each of these inputs is represented by the numbers or the numerical representation of our sequence, right? Okay, that's why. Did I make sense now, or more or less? Mm-hmm.
For example, the data we're training today is curated so that they are all 500 listeners. So in theory, it's easier for the model to just.
Exactly. In this case, we are padding them. We are adding, in this case, ones to their numerical representation of the sequences, so the model can accept this input. Yeah. But I am adding this because there could be some cases if you want to use this code as a template for your experiments, you can use it to pad them or to truncate them. Yeah. Yeah. Any other question up to this point? No? Okay. So then all we have to do is just to call the train method of the trainer object. Oh, well, you have to execute the trainer. Oh, no. Where is this? Oh, no. Oh, here it is. Sorry. I didn't execute the tokenize function, and the I didn't create it. I didn't create the tokenized datasets object. That's why. So what this is doing here, it's just converting this character or text representations of the sequences into the numerical representations of the sequences, right? So it is doing it for first the training set and then the test set. Then we will define the evaluation metric, which in this case is accuracy. And well, we are actually using another library from HuggingFace, which is evaluate. There are many available within the HuggingFace hub, and you can check all the others here in this website, right? So after we declare the training arguments, we can actually build the trainer object. And once we do this, we can finally put the model to train. And since we are using a GPU, this training process is accelerated because the training processes is parallelized. In this case, I put 5 epochs just for the illustrative purposes of this workshop, because normally genomic language models are trained for hundreds or even thousands of epochs. Yes?
Can you go over the logic part in the metrics function?
Where, sorry?
So in the compute metrics function,
Yes?
you have logic and labels picking something from eval creds.
Yes?
So the logic part, can you go over?
Oh, yes, the logics part. The logics, it's the raw output from the models.
So it's like compare with the actual, the predicted versus the actual.
Exactly, yes. The logics is this raw output that it might not have any kind of meaning in first place, but after doing some transformation with this output, for example, applying it a softmax or function or some kind of other activation function, we can convert these values into meaningful percentages, let's say. So the model is going to predict the percentage of a sequence being an enhancer or a non-enhancer, right? So while we wait for the model to train, here it just finished the second epoch. Does anybody have any other question?
So are we using a pre-trained model?
Yes, we are now using a pre-trained model.
So it's fine-tuned?
It's fine-tuning, exactly. Yes. The difference between training and fine-tuning is that in the fine-tuning process, we already have a pre-trained model, right? And we are just adjusting it to the specific application for our data set, right? The training phase or normal training means starting with randomized weights, parameters, etc. So in this case, we are just fine-tuning the model to predict between enhancers and not enhancers.
Can you fine-tune it in like classes that aren't in the model?
Yes, yes, you can, because the whole point of fine-tuning a model is to not create a new one, and to train it for hundreds or thousands of epochs. And because there is already research about the carbon footprint of training large language models, and there is information saying that training a model like ChatGPT, well, the carbon footprint is larger than 3 or 5 cars in their whole usable, or in their whole life, let's say. Yes, it's really important now, and now the paradigm, some people is changing the paradigm to fine-tune instead of training from scratch. Yes.
So like if you wanted to do this for a totally different species, not human, something that's not in the training data, you fine-tune it on a different species.
Yes, actually, in the paper of hyena DNA, they compare the model's performance between human and mouse. Yes, and it's really interesting what they found.
Could you do something like fruit fly?
Sorry?
Could you use a different species that's not in the training? So like fruit fly, or I don't know what's in the training actually. Is it human only?
In the training is human, as far as I remember. But the magic of fine-tuning is that there is already knowledge, let's say, within the network that makes it able to just adjust its what it has learned for a new species. Yeah. Yeah, it's something really handful from genomic language models. So it already finished training for 5 epochs. So the next phase of the workflow. Yeah.
Looks like it needs 2 hours for me, but I didn't say that.
Oh, did you configure the runtime type into GPU by any chance?
Oh, maybe I missed that. Was that at the beginning?
Yes. Yes, because when you select the GPU instance, there is a T4 on the upper right. Yeah. So, well, Oh, so to change it to GPU, here, you have this little arrow here on the upper right corner. You click it, and you click on Change Runtime Type. And here you select tip for GPU. And well, this is a good example of what happens if we are not using a GPU. You were saying that it takes, or the estimated time is 2 hours, right? The estimated time was 2 hours, right? And here the training was completed in 4 minutes. That is the difference of using a GPU or a hardware accelerator. Yeah?
How come the validation loss bounces back up?
You mean here?
If he was going down, then
Oh, yeah, I expected this to happen. So even though we are using a pre-trained model, there is some kind of randomness. There might be someone here in the audience who got a better result than me, or than you, or yeah. So this could be just because it is adjusting the weights, and it needs more epochs to get better at predicting the values, because again, we are just doing a fine-tuning. Yeah.
But in general, the difference between the results is small or big?
Again, sorry?
You mean that you can get different results, right?
Yes.
In general, the difference between the results are small. The difference between
It depends. It depends. It could be really variable. In this case, I didn't put a random seed or a random value for reproducibility because, well, I just wanted to check what comes out in different iterations. Yes. So, yeah. It's decreasing. Yes, exactly. Yes. Yes, this could be random. For example, when I was preparing the workshop, there were times where it was getting better, and and times like this that the accuracy was going down. So it is basically just one way to attack this problem is to augment the number of epochs and see if the model eventually gets better at the predictions, right? Or another strategy is to set up, a patience variable. So if the model doesn't get better or at its predictions in an n number of epochs, stop the training and just use the model as it is. Yes, that is another strategy. This is, again, for illustrative purposes to show you how you can implement these tools for your research. Yeah. So after the training phase, we can evaluate the model's performance. And there are many evaluation metrics that we can calculate to assess how the model performed along the training phase. So first, we are going to extract the evaluation metrics from the history log of the model, right? And then save these values into a losses and accuracies lists. So here are the first ones, the first evaluation metrics that we are going to see: accuracy and loss. The loss value is a value that tells us how far or how different the model's predictions are from the ground truth labels, right? The smaller it is, the better predictions the model is giving us. And for accuracy represents the percentage of correct predictions out of the total number of predictions. So ideally, this is how accuracy and loss will look like along the number of epochs, right? Loss should go down and down and down. It never gets to zero because it's, well, practically impossible to get a perfect classifier. And the accuracy goes up, but never touching 100% accuracy. Right? Mm-hmm. Yes. Yes, it's not always the case because there exists the possibility that the model overfits to the training data. So the model, the more epochs you put for the training phase, the model actually memorizes, kind of, the structure of only the training data set, but doesn't generalize this knowledge for the test set. So these are some strategies to control the model's performance. If there is a point, let's say epoch 24, in which my model achieved 80% of accuracy, and I have a patience metric or a patience variable for another 5 or 10 epochs, and if the model doesn't get better in those 5 or 10 epochs, it just takes the current state of the model on epoch 25, I said? Yes, and that's it. Mm-hmm. Yeah, because there exists this possibility that the model is actually not learning, but memorizing the training data set. Any other question? Yes?
In this plot, what is the range of the x-axis?
What is the range? It could be just the number of epochs. It's variable. You can train a model for 20, for 30, for 50, for hundreds of epochs.
Yeah, so for example, at which point in general we would expect 80% accuracy?
It depends on the model and the data. Yeah, it's variable. Or at least it's what I have found in my experience. Yes?
Is there any facility to save the best model, like Keras? Can you save the best model?
Yes, I didn't implement it here in the workshop. That's a really nice idea. I will try to include it. You can check the notebook later, and I will implement that. But yes, you can save the model states dictionary for the best instance of the model on the epoch number n. Yes. Yes. So when we extract these values from the model's metrics, well, we can see that we didn't get the ideal behavior, and it actually performed worse along the training phase. So, yeah, I should have put a random seed just to make it reproducible. But okay, maybe somebody got this line going up with the number of epochs, sorry, and the loss going down eventually with the number of epochs, right?
So here, the ideal number seems to be 2, or 2 epochs with the best accuracy.
Yeah, in that case, exactly. But there are some times that, again, if I put, let's say, a patience of 5 epochs, maybe in the next epoch, if I put, let's say, 10 epochs, on epoch number 6, the model gets better than that. As it is also very related to optimization problems, it is searching the best combination of parameters within a search space, which is really, really big. Yeah. So another way to assess the model's performance is with a confusion matrix, right? This is a metric that quantifies and shows the number of correct predictions against the incorrect ones. Here we have 2 axes. As you can see, the vertical axis are the real values, and the horizontal axis is the real values, and the vertical axis is the predicted values. For example, here in the first part of the matrix, we have the true negatives. In this case, the number of sequences that are not enhancers detected by the model. On this other part of the matrix, we have the true positives, that in this case means the number of enhancers detected by the model. And we have the false positives and false negatives. For this application, the false positives mean sequences that were classified by the model as enhancers, but they are not enhancers. And the false negatives, sequences that were classified by the model as not enhancers, but are actually enhancers. Am I making sense with this? Okay. So how do we calculate this? We have to generate a set of predictions here, and then we will use again the HuggingFace's evaluate library, but now we are loading the confusion matrix metric. So we run this cell, and here the model is just generating a set of predictions again on the test set, and here is our confusion matrix. In this case, for example, the model predicted 2,418 sequences as not enhancers that at are actually not enhancers, 2,578 sequences as enhancers that are really enhancers, and we have, for example, 896 false negatives and 1,056 false positives, right? This is another metric that could tell you, well, if the model is performing okay, if it's not okay, right? Another metric we can check for the model's performance is the receiver operator characteristic curve. And this displays the true positive rate against the false positive rate. This one tells us basically how likely is it to detect a true positive, in this case, detecting an enhancer that is actually an enhancer against the false positive rate, meaning that the model, its predictions are not accurate for enhancers in this case. So in this case, we are now calculating this ROC curve, and we got an area under the curve of 72%. This means that 72% of the time, the model will detect and predict correctly enhancers. Okay. Any question to this point? No? The better, the higher this curve is, the better, right? If we got an area under the curve of 1, it will mean that we have a perfect classifier, which is practically in implementation impossible, right? And if it is in this dashed line, it means that we have a random classifier. It is like tossing a coin, basically. So here is a little summary on this and more evaluation metrics, right? Here are some abbreviations for the true positives, true negatives, false positives, and false negatives. So the first one is accuracy. This represents the number of the total number of correct predictions out of the total number of predictions, including false positives and false negatives. The second one is the sensitivity, the true positive rate of models test. This means how many of the enhancer sequences were actually categorized as enhancers. In this case, we will take from the confusion matrix this metric, this number. The numbers that you are looking at here in this text are the number of samples that I got when preparing the workshop. For the specificity, this one means or gives you the information about the proportion of sequences for this problem that are not enhancers and were correctly classified as not enhancers. So this gives you information for both sides. This gives you the information of how many true positives you have and how many false true negatives you have from the model. This is important to check what are the model's capabilities to differentiate between true samples and negative samples. Finally, we have precision, which takes in account only those samples that were classified as positive, including true positives and false positives, right? Here we have another time the receiver operator curve and confusion matrix. Does anybody have a question up to this point? Yes. Okay, here.
In our case, is that an acceptable rock curve, or would you want more to fine-tuning the model?
You should, in this case, we should continue fine-tuning the model. Normally, or on what I have seen, is that an acceptable rock curve is around, it's above 90%.
Would you approach it by changing
That will be one strategy, yes. Yes, another strategy is getting more samples. That is another one. Because what you want to do with a deep learning model is give it the most examples as possible, describing the phenomenon you are studying. Mm-hmm. Yes, yes. If the model is not performing as you expect, this could be two initial strategies to tackle the problem of low accuracy and high loss values, and also an area under the curve of 72% or lower. Mm-hmm. Mm-hmm.
I think usually you have a parameter, you can get a curve, whereas in this case, just a single point. So I'm wondering if there is something we could change in the model that maybe in the final layer in order to get more sets of predictions.
You mean to classify more samples or include different classes?
Parameter we could change at the end of the network in order to get more sets of predictions. Like now we have one set of predictions that gives us 72% or 72 area under the curve. But how can we get more without changing the model? Is that possible in this scenario? For example, in logistic regression, you have this threshold at the end. And changing the threshold, you can control how many, you can even introduce some bias. But here, is there something similar here?
To be completely honest with you, I don't know. But that will be a really nice starting point to check, because something like that never came to my mind before. Yeah, so to be completely honest with you, no idea. Yes?
What adjustments did you make if the data set was imbalanced? Would you, for example, would you adjust the model?
Sorry, again?
If the data set was imbalanced, would you adjust the model in some way, or would you oversample or downsample?
If the data set was imbalanced, one strategy is to do data augmentation. For example, if you, let's say that in this case we had 1,000 samples for enhancers and 500 samples for not enhancers. There are some methods that help you to generate artificial samples based on the characteristics of the class that you have less samples from. Am I making sense? Yes. That could be a possibility if you have an imbalanced data set. The problem with it is that they are not real samples from the phenomenon that you are tackling.
Can you penalize the weights and so on in the model that you can in some other types of?
P-analyze the model?
Can you change the weights? As in, can you adjust the weights such as to account for the imbalance or not really?
Maybe you can, but that wouldn't be ideal, because if you move a parameter, you basically move or change the model's predictions. That's why it is done iteratively with the training phase. Because these changes could be really subtle. They could mean nothing for us, but they mean something for the model. This subtle change, and yes. Mm-hmm.
And when would you decide you want to try a different model, or you keep fine-tuning? How and when would you decide, would you choose a different model to fine-tune, or keep fine-tuning the one you're already working on?
Well, that is a really nice question. For my first approach would be, if I already tried everything I could do to tackle these problems or these problematics, and the model doesn't get better at predicting these values, I will look for, if I want to fine-tune a model, I will look for another one there directly, yeah. Fortunately, nowadays, there are many genomic language models. Hyena DNA is just one of them. And again, this is because of its, I'm really sorry for the computer. Hyena DNA is not a transformer because of its architecture, but there are many other powerful architectures out there. For example, one that comes to my mind is DNA-BERT. It has two versions, DNA-BERT 1 and 2. There is another one that was developed by NVIDIA, that is the nucleotide transformer. It's one of the biggest ones, that one. So you can try many different models. And again, thanks to Colab and many cloud options that we have nowadays, implementing these models is really straightforward. And if you really want to get into the inside, to the, let's say, organs of the model, you can create yours. But this is really, it's a difficult task. Yeah, because they are as Lego structures. Maybe there is somebody that likes Legos a lot and makes really nice figures, but as maybe somebody has seen in social media, there are whole projects about Legos, right? So it's, we can take the same ideas. So you can construct or can build really basic and useful architectures, or you can construct really complex and hard and robust models as well. So is there any other question about this? No? So I guess we will have the 15 minutes for a break, and we will come back and well, now check how can we actually train and construct and build a model from scratch. Thank you. Okay. Thank you, everybody, for coming back. And let's resume the workshop. So I hope everybody's instances were not disconnected. You can check it if there is a tick here, everything is fine. Does anybody's instances were disconnected by any chance? Yours? Okay. In this case, what we will need to do is reconnect to the T4 instance, and then execute this cell and this other cell again, and that will be it for now. Okay. Okay. So continuing with the workshop, the next part is training a neural network built from scratch with PyTorch. PyTorch is one of the most used frameworks for deep learning recently. It is developed by Meta, the company that owns Facebook, WhatsApp, Instagram, and etc. And well, we will look how the actual model is built and how to prepare also the data set to be compatible with the PyTorch neural networks and the data loaders objects. So let's go back to the notebook. Oh, sorry. I have to. Okay, there it is. Okay. So let's scroll down. For those people whose instances were disconnected, were you able to reconnect them? Yes? Okay. Everything that you need to do is, again, just reconnect the instance, select the T4 GPU instance or the hardware accelerator, and then connect and execute these code cells just to reinstall the libraries and import the libraries again, okay? Because we will be using them again. So as you can see here, there is a table of contents. Just to not scroll all the way down, select this section, training a PyTorch model with your own data. Here, this is another example of how to train a deep learning model, but built from scratch, from the data as well, right? Here, we will work with now coding and non-coding sequences. And I am giving you, or I am implementing this data through a CSV file. So maybe it's the most common file format that we can find in data science and deep learning workflows, etc. So the first step is to download this file here by executing this code cell. And as we can see here, we have sequences and values, right? And now we have sequences with different lengths, right? This one will be a little bit more complex, but now that the ideas of the workflow are, well, I hope clearer, we can understand what is the workflow for this next implementation. So here we already have our sequences and their corresponding values imported, right? And do you remember, just before going to this, do you remember what was the step before giving these sequences to the model? What is the step that goes next to the data importation? Yeah, tokenizer, right? The HuggingFace tokenizer was already giving us the sequences in the expected form by the model. But when we are implementing these deep learning models from scratch, we have to take more elements into consideration. For example, PyTorch neural networks expect us to transform these sequences or inputs into a data structure known as a tensor, right? A tensor, let's think about it of a 3 or more dimensional array, right? So basically here we can just look how to declare a tensor, how to create a tensor. We can check that they have many methods for their manipulation. We can do also many mathematical or arithmetic operations with them, etc. If anybody has used NumPy for linear algebra or any other application, getting used to tensors won't be really hard. But the difference between PyTorch tensors and normal or conventional NumPy arrays is that they are already optimized for this backward optimization that they explained us yesterday, that there is the rule of chain and all the calculation of the derivatives that we saw yesterday. Do you remember? So these tensors are already optimized for that kind of calculus, right? So here are just some examples of the methods that, or strategies or things that we can do with tensors. We can print the data type they have, they are storing in their data. We can transform this data into another kind of data type, and we can also do some kind of multiplications or arithmetic operations with them. Okay, so here's where tokenization comes handy. We will use again the tokenizer from the Hyena DNA model, but this is just for, again, illustrative purposes, but you can actually build your own tokenizer. In this case, the Hyena tokenizer is just a single nucleotide tokenizer. This means that, for example, adenine is assigned to the value of 6, cytosine to 7, guanine to 8, thymine to 9, etc. Right? So each of the nucleotides is represented by a single number in this case. But there are many other tokenizers that could be K-mer-based, maybe, or they can have many other combinations of words, let's say, that take these words as a single number, right? In this case, we are just using, again, the Hyena DNA tokenizer. To train a model from scratch, well, we don't have to worry too much about compatibility between the model and the tokenizer because we are starting randomized parameters and weights in the model. So again, we apply the tokenizer to the sequence in the dataset, and we can see here that it gives us back another dictionary structure that includes the input IDs. This is the sequence represented in numbers, right? And if we scroll all the way to the right side, we will see all the elements converted into numbers now, right? Now we can decode these input sequences just to check how the model will see these sequences. And as you can see, as you may see, there is something new here. This is called a special token. This is what the model takes into consideration when it looks to different batches of information to differentiate between sequences. So it doesn't take 8 sequences as one, right? This is again part of the natural language processing workflow. So if we just want to take back or produce the PyTorch tensors, we can just add this parameter, return tensors equals PT. It's equivalent for TensorFlow as well. And here we can see input IDs equals tensor and the input IDs corresponding to this sequence, right? But this is only one sequence. How can we actually transform the whole data set or the batches in which we are going to feed in to the network. So this is done with the data set and the data loader objects. And maybe this is the hardest part of the workflow when you are implementing a deep neural network from scratch. Here, this code that looks horrible it's just to declare a new class, the dataset class for the dataset. Basically, we have three functions. First, init, that declares or initializes the properties for the dataset. Second, the len, that just returns the length of the dataset, and the getItem function that tells or indicates how the data is going to be retrieved from, let's say, from our pandas data frame, right? So here I just declare some parameters and some properties for this class, and here I initialize them, right? I already put a method or a parameter that is split if I want to retrieve only the train set or the test set correspondingly. And the getItem is what gives me my sequence and my label together and compatible for the model, okay? So once we execute this cell, we won't get anything from the output because it's just the declaration of the new class. But the magic happens here when we actually initialize it. So again, we don't get anything from the output here because this is only, let's say, storing the data from the data set, already split it into training and test set, right? And maybe I am not going into the details of this class because it's a little bit, it's long, and I will need more time, but you can take this as a reference if you are working with your own data set and how to implement your data set and convert it into a PyTorch data set, because are different objects with different properties within the workflow. So now that we have initialized our data sets, we define a batch size, right? This is the batch size or the number of samples that will be given to the model in each iteration. And after this, we declare or we create the data loader objects. This grabs the dataset object to take, in this case, 8 random samples from the test set or the train set. So this is why we put the shuffle parameter here equals to true, because we can take 8 random samples from the whole data set at each time and feed it into the model. In the case of the test loader, we have this same variable shuffle equals to false, because we are going to make the predictions or produce predictions with the model, but we always want this to be reproducible, and we want to check how well the model is generalizing the data from the training set. Any question up to this point? Yes?
When you set the shuffle to true, the program split the eight samples into 4 from one class and from.
Yeah.
Oh yeah, well I'm gonna repeat it. So when you turn the shuffle true, or when you have the shuffle true, does it makes the batch size to take like 4 samples from one class and 4 samples from the another class, like a balanced batch, or it's like random? It could be 5-3 or 7-1.
It is random.
It is random.
Yes, it is random. That's why. That's another reason why we need our data set to be as balanced as possible.
And is there a way to make it like perfectly balanced, like to take half of the batch size from one class?
As far as I know, there is not a way.
Okay.
Yeah, it's completely random. Then the samples that it picks from the data set.
Okay, thank you.
Yeah. Another question?
Why do you not shuffle the test set?
Oh, yeah. So the people
Why
in
do
the
you
last.
not shuffle the test data set?
Why I didn't shuffle
Yeah.
the test set? So the predictions could be reproducible after it. Every time I want to make new predictions to evaluate the model's performance. Yeah. Another question? No? Okay. So just to see how these data loaders objects work, we can print a batch here. As you can see here, I print the batch number 0, and here are 8 samples of the inputs, and all of them are in the tensor form or the tensor data structure. This is how the model actually expects the inputs to be, okay? And it is worth to mention that the labels have to be as well in the tensor data structure. Another thing that I didn't mention is that the inputs and the labels have to be in the same, most of the time, have to be in the same data type. As you can see here, we have a float type, right? Because we have a decimal point. And if we don't have the labels and the inputs in the same format, the model is going to struggle with making predictions. It is going to throw at us many errors, and we could be in this process much time, and it will be only because the tensors between, or the formats between the inputs and the outputs are not in the same format. So this is something to take into consideration when implementing a deep neural network from scratch and when preparing your data set, okay? So now we train the model, or we build it to be more precise. And here comes another stack of code defining the characteristics and the labels, and the layers of this model. Again, we have to define a class that, how do you say this? That inherits from the nn.module library from PyTorch. This is to make this class, to adapt this class and add all the methods and functions related to all of those blocks in the nn.module library. So we can import all those functions at the same time just by adding it as a parameter here, okay? And we have here 2 basic functions when defining a model or a class for the model. We have the init, which defines the number or the characteristics this model will have. In this case, we are just assembling a simple model, convolutional model, with only 1 convolutional layer and 2 feed-forward layers for the classification. So if we execute this cell, we won't get anything in the output, but the genomic CNN object is already existent or exists in this Python interpreter. Okay, so just to give you a little overview about this architecture, here we have the first convolutional layer that has its parameters and takes these values from the init function, from the init parameters, then a pooling layer that pulls the max values from these convolutional operations, and then a flattened layer that makes these 2-dimensional outputs and converts them into one large 1-dimensional array to finally fit them into the linear layers, right? And since we are going to predict a probability, we are going to hard code in some to this instance into 1 output unit in the output layer, okay? In the forward function, we just define and indicate how the information is going through the model. Okay. Any question about the class and how it is defined? No? Seems like there is not. Okay. So continuing with this, we are almost there to train a manually implemented model in PyTorch, right? All we need to do now is to define or to initialize a device. This is where all the math happens. That's why we are, well, I am asking you to put the runtime type into T4 GPU, so the training process could be accelerated. Then a loss function. Here, we didn't put this in the trainer, in the HuggingFace's implementation, right? Oh, do you have a question? No? Okay. So this loss function tells you how much is the difference between, the predictions and the ground truth labels, right? The number of epochs, again, how many times is the model going to see the samples within the training set. The optimizer, this is a way of calculating and updating the model's weights and parameters to yield always increasingly better predictions. And the training and test loops. This declare how the information or how our inputs are going to be processed through the network. So that's what we do here. Here, first, we define the device that we are going to use for the model. In this case, CUDA means that we have a GPU, more specifically an NVIDIA GPU. If it is available, here there is a method in Torch or in PyTorch that detects if a GPU is available. The MPS, it's another, let's say, characteristic. This is specifically for the Apple Silicon chips. They make or they adapt the operations to be processed on the GPU chip within the MacBook Apple Silicon chips. And if neither of these devices is available, we are just going to use the CPU. Here we define all the parameters or the input parameters that define the structure of the model, the kernel size, the input channels, the output channels, and everything. So you can tweak them as you want. That's why I put them here, so you can change these values as you want to check if you get better results or worse results and how to tweak this network. And since we are working with a model built from scratch with randomized parameters and weights, first we wouldn't expect too much accuracy from the model. Okay. Here we initialize the model object, and here we define the loss function. So we are going to use the binary cross entropy loss. This is a really optimized loss function for binary classification problems, as the one that we are tackling here. And we define the learning rate. This is, again, if you may remember from yesterday, how subtle or how aggressive the changes in the search space for the best parameters are going to be in the optimizer space, right? And finally, define the optimizer. And maybe you didn't see these parameters or these hyperparameters, better said, in the HuggingFace implementation, because the HuggingFace implementation is created to make the application of deep learning models straightforward. If you don't want to deal with many or technical things about this kind of hyperparameters, you just put the number of epochs and that's it, right? So once we declare this or execute this, we look that we are going to use a CUDA device. This is why we have the T4 instance in Google Colab. And here there is basic information about the model we are going to use, right? So we have, again, a convolutional layer, the max pool layer, the flatten, and the two linear layers. What is next is to define the training and the test loops. They are basically the same. The difference is that in the train loop, we configure the model to training mode. It basically tells the model that, hey, you are going to train, so you have to calculate the loss and adjust your parameters in order to yield better predictions. So here's what we do here. First, we send the model to the device, in this case to the GPU, configure it to training mode. Here, this is only the size of the data of the train loader, just to keep track of in which phase the model is training. And here, we are just passing the inputs and outputs to the model, getting predictions out of the model, and calculating the loss for the predictions compared to the labels in our data set. Then it makes the calculation of how far or how wrong our predictions are from the labels and adjusts the parameters. Finally, we zero these gradients, or we reset the optimizer for the next iteration, and we print the model status every 1,000 samples. That's what we do here by defining the training loop. The test loop, this is more or less the same. We just configure the model in evaluation mode instead of training mode. This is telling the model that, hey, you're going to just make predictions because we are trying to assess how well you are performing, right? If you look at these blocks, they are almost exactly the same, right? And we are here calculating the correct number of predictions, and that will be our accuracy, right? Within the test loop. So once we define these functions, we already created these functions in the Python interpreter for this instance, and we can call them. All that we need to do now is define the number of epochs. That, again, is the number of times the model will see the training data. And we are going to create these empty lists to save the values of the losses and accuracies to plot them, and that will be it. So once we execute this cell, the model is going to train again, but now for 10 epochs. And again, this model is randomly initialized, so we wouldn't expect good results from it because it should be trained for hundreds or thousands of epochs to generalize the information from the data set, because evaluating or tackling genomic problems or biological problems in general are very complex phenomena, and many variables have to be taken into account, right? So I guess the last time I got, I think, maximum 8% of accuracy, but it was increasingly going up, right? So the first epoch just finished, and it got 7% of accuracy and an average loss of 0.86, blah, blah, blah. So while we wait the model to train, anybody has questions about the whole process of the implementation from scratch of deep learning models?
Is it the same like process for all models, or is it just for like if you want to use a different model, would you set it up differently?
Could you repeat it, please, for the people in the live stream? Yes.
Sorry, is this the process and steps, is it the same for this particular model, or you can just sort of copy and paste and use different model?
You can copy and paste it most of the time. This is the same process. Maybe if we were using, again, a HuggingFace model and using our personalized or custom training and test loop functions, maybe we should change some things, for example, the outputs, because the way the outputs are produced from my manually developed model is different from those in HuggingFace. But the process is pretty much the same. Yes. Any other question? No?
Excuse me. I might have missed it, but are we using 8,000 samples per bus? So we have 3 buses per epoch. Is that how we can read the messages?
Again, I couldn't understand very well.
It looks like they're doing, from the messages, it looks like we have 3 steps on each epoch. Is that because we have batches of 8,000 samples?
It's because of this statement here. Here. Every 1,000 batches, yeah, we are looking at the state of the model. Yes.
Okay, and is there a parameter to control the size of the batch?
Mm-hmm, exactly. Yes. For example, if I put here every 100 batches, we will see more lines here. Yes. We can try it later just to clarify this detail, but it is printing the state of the model or the loss values and in which iteration the model is performing right now every 1,000 batches.
But on a different point, can we control the size of the batch?
Of the batches? Yes.
Yeah, like
yes,
how
we
many
can.
sequences? Is it somewhere at the beginning of the...
Yes. Here it is.
Oh, okay. Sorry, I missed that. Yeah, this is what I was looking for.
Yeah, a batch size of 8 samples is actually really, really tiny. Normally, you will see something like 32, 64, 128, yeah. This was, again, only for the illustrative purposes of the workshop. And, well, it is going now on the epoch number 5. And maybe
Sorry,
here
can I just ask a quick question from the YouTube chat? Could you provide more details on how the architecture was selected for the CNN?
Oh, how the model was picked? Or
yeah,
why did I decide?
On how the architecture was selected for the model?
From the class? Well, in this case, if they are asking me the reason why I picked a convolutional architecture for the workshop is because I wanted. Yeah, that will be the answer. But the actual details of the convolutional layer, you can get more information on the PyTorch website. I just wanted to give an introduction of how an architecture in PyTorch is implemented from scratch, because in this case it's a convolutional layer or a convolutional neural network, but I could have chosen maybe a recurrent neural network, a simple transformer, or even a multi-layer perceptron for the workshop. Yeah.
Thank you. I hope that answered your question, Manuel.
Yeah. Any other question? Yeah. Mm-hmm.
Sorry, if you use the bigger learning rate, will it run faster, the model?
No, the learning rate is how is the rate of change in the space field of solutions for the optimizer. If I select a bigger learning rate, maybe my parameters won't be, or maybe the changes in my parameters will be graded as well. And this could mean for the model either better predictions, or the predictions will be completely worse. So basically, the learning rate is telling me how aggressive the changes in my parameters will be. Yes. So normally, if we are speaking about time, if you are training a model with a really tiny learning rate, maybe what you should do is increase the number of epochs. Yes. But it is recommended a little learning rate so you can get more control of your model's training. Yeah. Any other question? Did I answer your question first of all? Yes. Okay. Any other question? Okay. This is almost done. And as you can see here, you might detect that we have increasingly and decreasing accuracies between epochs, and this is quite normal, right? On these huge models like hyena DNA, I remember that in the paper they said that the model was trained for 3 weeks with a batch size of, I don't remember, but it was huge. With a learning rate really tiny. So for biological applications in deep learning, it takes time, right? And again, these hyperparameters that I put here in this workshop were just to show you how to implement these tools for your research and just give you a starting point of how you can start implementing these strategies for your problems or your biological questions, right? So it is about to finish. There it is. There it is. Okay, so now we evaluate the model. We can check how reliable it is. We move the accuracies values to the CPU because they were being calculated in the GPU. And now we check the evolution of the loss value and the accuracy value. And here we can see something more similar to the ideal waveform that I showed in the beginning, right? It is not as pretty as the other one, but eventually it becomes better. Or I think someone got something really strange here, did you? Yeah. Oh, yeah. Yeah, that happens again because the model is randomizedly initialized. Yes. So in this case, maybe someone got better results than me or worse results than me. So we can use the same evaluation metrics for both models, the HuggingFace implemented one and the manually implemented one, right? So again, just to check or calculate the confusion matrix, we generate a new set of predictions. Here we save them into a variable named ypred, and calculate the number of correct and incorrect predictions. And here we have our confusion matrix. That is not good. It is not good, to be honest with you. We have many false negatives here and many false positives here. So, but again, if I put a lot of epochs, maybe my model will develop better prediction power and will get a better accuracy and will yield better predictions eventually. And finally, the rock curve. We can check the odds of picking or predicting correctly a coding sequence from a non-coding one here, right? And the area under the curve here is 63. So we have 63% of probabilities of picking or predicting correctly a coding sequence out of the non-coding sequences. This is again not ideal, but one of the strategies to increment these values and to increment the relationship between true positives, true negatives, false positives, and false negatives is add more data to the data set or increment the number of epochs to start with, right? So is there any question about how the evaluation metrics or how we can how can we take meaning out of them? Mm-hmm.
Sorry, I missed it. So for the evaluation, you only evaluated the last iteration, or?
Sorry, I might mislead. So I'm wondering, for all these evaluation metrics, do
Mm-hmm.
you only test the last iteration, or you would test all the epochs?
Oh, I just tested on the test set of my data set. Yeah, because the epochs is the number of times the model sees that only the training set. It is trying to learn the structure, to find some kind of how is it called? Sorry. Yeah, it's just trying to learn the structure and generalize the data set and how can we test the model's capabilities. Yeah. Making predictions, some data that the model never saw during the training phase.
And the follow-up question would be, for example, if in the accuracy plot you see an increase and then drop, can you test the model? Say, for example, can you test on the model after 9 epochs rather than after 10 epochs on the testing data set?
Yes, you could. Yes, we will need to add more epochs only to the training phase,
okay,
and just and evaluate after that epoch finishes.
And what we're doing now is the final model.
Yes, the final model, the model that was trained for the epoch number 10.
Thank you.
Mm-hmm. And in this case, we really got 7%, almost 8% of accuracy. That it's almost nothing, right? But again, this is just to give you an idea of how can you implement these tools and how can you tweak and personalize these models to your own preferences or necessities, right? So here's the conclusion. I hope that in this workshop you learned something new. I learned something new today as well based on your questions. And we implemented 2 different deep learning models with different architectures and complexities to classify genomic sequences for 2 problems. The first one was to differentiate between enhancers and non-enhancers, and the second one was to classify coding sequences from and non-coding sequences. The first model was retrieved from the HuggingFace hub. It was implemented with all the functions and helpers that are available in this library. And the second one was, well, manually constructed, built from scratch, and trained from scratch out of from randomized parameters. And we learned how to construct the data or the essential objects as the data set, the data loader, and the actual model. Since the workshop is focused on showing you how to implement these techniques, well, if it's of your interest, you can save this Jupyter notebook or keep checking it whenever you want. It will be there. It will be on my GitHub repository, and I will be giving it some updates, so you can check it from time to time. And if you are executing it in Colab out from the GitHub repository, and if you change something that breaks the code, well, the only thing that we will need to do is just reload the page and everything will start working again. So, well, these are my contact details, just in case. And maybe just telling you, just close, talking about a little bit of me. Well, I am just a PhD student in computational intelligence at the University of Guadalajara on the University Center for Exact Sciences and Engineering. And well, I also did an exchange to the Free University of Berlin during my master's, and I learned a lot of these things over there. And I am part of the Biodigital Innovation Lab at University of Guadalajara in the same University Center. And this is our logo, and this is the team that I work with. And well, I am just the deep learning guy in this lab, but we do many stuff, many crazy stuff, and well, hope you can check our LinkedIn to stay tuned for our publications and stuff. And here is our Instagram if you want to follow us as well. And well, this information is also on your notebook, so you can ignore it if you want, but I hope you don't. And well, these are the references that I took for the workshop, and maybe you can check them for the reading. And well, we actually finished pretty early, but I thank you all for coming to this workshop, and I hope you enjoyed it, and learned something new. And that will be everything from me. Thank you so much.
There's another question on the chat, actually, if I can just ask that. If one would want to understand what part of the sequence separates coding from non-coding sequences, how would you recommend doing so? And also, thank you for the great presentation.
Sorry, I couldn't hear very well.
If you'd want to understand what part of the sequence separates coding from non-coding sequences, how would you recommend going about finding this out?
Oh, so let me see if I am understanding correctly the question. So basically, they want to check which part of the sequences make them coding and which part of the sequences make them non-coding, right?
Yeah.
Well, in this case, we will, since this is a convolutional neural network, maybe we can extract the weights of the most representative kernels in the network, and that will give us a hint of which subsequences, let's say, are the most important for the classification problem.
Wonderful, thank you. Lovely. Oh, if we can give Moises another round of applause. Thank you very much for taking this workshop forward.
Thank you.
And I know we did finish a little bit early, but lunch will be served at 12:30 on the other side of the auditorium. So yeah, just feel free to go and grab a drink for now. And if it's okay, ask Moises any more questions if you fancy catching him after the workshop.
Yes.
Lovely. Thanks, everyone.
Thanks, everyone.